Welcome to our lesson on kinetic energy and the work energy principle. In this lesson, we're only going to discuss translational kinetic energy. One thing that's very important for you to understand about energy is that it is a conserved quantity. What I mean is that while we continue to discuss energy and work, we're going to talk about kinetic energy being transformed into potential energy and vice versa. But in reality, the total energy in a system stays the same. That said, even if potential energy changes to kinetic energy or kinetic energy changes to potential energy, the sum of those energies should always be the same before as it is after some kind of situation. Now, for just simple translational mechanical energy that we're discussing in Physics 1, then we can define energy as the traditional ability to do work. This simple definition is not always applicable, but for mechanical energy, like I said, it is applicable for these situations. Now, let's consider a moving object and like a flying cannonball. It can do work on a brick wall if it actually knocks the brick wall down. All right. So what I'm saying is if you throw a rock at a wall and nothing happens to the wall, then no work was actually done on that wall. But if you hit a wall with a cannonball and the bricks actually fall, then the cannonball did work on the wall because of the fact that the bricks moved. So what I'm saying is, and we discussed it before, that the quantitative definition of work is, I'll write it here on the screen, work is equal to force times displacement. Now, of course, you need some force, and you need an object that has some force with it. But you also need whatever it strikes or whatever it comes into contact with to move. All right? If that object does not move, then no work is done. All right? So it's the same thing with a hammer and a nail. If you hit the head of a nail with your hammer and the nail drives into the wood, then you have displaced it and therefore you have done work to it. But if you have a little toy hammer and you barely tap the nail, okay, and the nail does not move, then despite the fact that you did apply some force to the head of the nail, there's still no work done because there was no displacement in the nail. So two things are needed. An object with the ability to actually apply force, and for the second object to move as a result of that applied force. So then, talking about the object that has the ability to apply force, in this case the hammer or the cannonball, we say that if it's moving, then it has the ability to apply force. And we can actually measure that energy that it has, that ability to apply force, if we have the mass of the object and the velocity of the object. So one more time, let me just run that back. An object in motion has the ability to do work, so we say that it has energy. In other words, energy, the energy of motion is called kinetic energy. So let's then discuss how we can write kinetic energy quantitatively. All right, because as we said, a hammer is moving and it has mass, so it has kinetic energy. How do we write that quantitatively? What's the equation for actually finding out how much energy it has? So first, I'm going to ask you to consider a simple rigid object like a car. Okay, so you see a yellow car here on the screen. Let's say that this object has a mass m, just like normal, mass m, and it's moving in a straight line with some initial velocity, v1, so we're going to call initial velocity v1 and final velocity v2 in this case. And we say that in order to accelerate it uniformly, specifically uniformly in this case, to a speed that is our final velocity, a constant net force must be exerted on it parallel to its motion over displacement. So if the force applied to it is constant, then the acceleration it experiences will be uniform. And that's really important because that allows us to derive some expression for kinetic energy using the uniform accelerated motion kinematic equations. And I'll show you exactly what I mean, because we're going to start with our quantitative expression or our quantitative definition for work. And we discussed this in the last lesson. It's that work is equal to some net force times the displacement of an object. And from here, we're going to go ahead and apply Newton's second law, because force is a part of our definition of work, and we know that according to Newton's second law that force must then be equal to the mass of an object times its acceleration. So together with the kinematic equation, v2 squared minus v1 squared, v2 squared is equal to v1 squared plus 2ad, which we can rewrite for acceleration. We're going to use these two equations, this equation here and this equation, which is just the rewritten version of our kinematic equation. And we're going to plug this expression, follow me here, I know I'm saying equation and expression a lot. We're going to plug this expression that we have solved for acceleration in uniform accelerated motion in for the A in Newton's second law. And we're going to take that whole thing and plug it in for F in our definition of work. And I'll show you that step by step. Now, don't forget that V2 is the final speed and that V1 is the initial speed. All right, so using the formulas we just discussed, we're going to start with our quantitative definition of work. And then we're going to say that because Newton's second law is F equals ma, we're just going to go ahead and plug ma in for force, which you'll see right here. Now, we can then say that, well, we used one of the kinematic equations for uniform acceleration to solve for A in this manner. So we're going to go ahead and plug that in there instead of the acceleration. And from there, we get to cancel out the displacement, and that's one of the reasons why this is very useful. We get to cancel out the displacement so that our new expression that we set equal to work is independent of displacement. And that's actually very important, and that's why we did this whole thing in the first place. We're always trying to cancel out things to make an expression independent of other variables to make it easier to find. So now we've canceled out our displacement, and we have that our net work can be equal to mass times acceleration in this manner, okay? And it's not acceleration because we canceled out a d. It's mass times this expression, okay? Now, we're almost done. Next, we're going to go ahead and distribute this m into this quantity, and it's going to give us this ratio that's kind of ugly. We don't really like it, but it does have two terms in the numerator. So because it has two terms in the numerator, we can kind of separate it out to make two ratios, this ratio minus this ratio, all right? And what's very important about what we've done up to now is that this first ratio has our final velocity, whereas this second ratio has our initial velocity. And other than that, they're basically the exact same ratio. All right, the only difference is that for one, we're plugging in our final velocity, and for the other one, we're plugging in our initial velocity. We're still using the same mass, and we're still dividing it by 2. So one more step just to clean this up, we can rewrite these two ratios to just be this expression here, mv squared times 1/2, because it's just the whole thing is divided by 2 in the first place. So now we have this final cleaned up equation here that says our work is equal to 1/2 mv2 squared minus 1/2 mv1 squared, okay? And so here's an important statement we're about to make. Now, what we have is the change between two quantities at two different velocities. And if we define kinetic energy to be the 1/2 mv squared, okay, then we can say two things that are extremely useful. So if we just define these expressions as kinetic energy, okay, then we can say that, first off, kinetic energy is equal to 1/2 mv squared, because we just decided to define it as 1/2 mv squared because it's helpful to us. So we're going to say that this is the quantitative definition of kinetic energy. And then, if that's true, then this is just the change between two different kinetic energies at two different velocities. So we can say that our net force is just equal to whatever the change in our kinetic energy is. And now we have derived and invented, of course we didn't invent it, but we have derived our work energy principle. And so the work energy principle is just that, okay? And I have it here in bold. The net work done on an object is equal to the change in the object's kinetic energy. All right, if you want that quantitatively, then it's just here, okay? We just derived it up there, but you see it here now, all right? So in conclusion, all right, the work energy principle is a very useful reformulation of Newton's laws. It tells us that if, and you'll see this in a couple of the practice problems, it tells us that if positive net work is done on an object, then the object's kinetic energy increases by an amount equal to the work that was done on it, okay? And that means that work and energy are both going to be in joules. This principle also holds true for the reverse situation. If the net work done on an object is negative, the object's kinetic energy decreases by that amount of work. So if the original kinetic energy was some number of joules and negative work is done on it, then you just go ahead and take those joules and subtract the joules of work that were done on it, and then you have your new kinetic energy. Let's see a quick example really quick. So you'll notice that there is a car here that was initially traveling at 20 meters per second, but then it's traveling at 30 meters per second some distance later. Okay? Now, just taking a quick look at our work energy principle here, if I can divert your eyes here, notice all of this stuff that we just derived makes it to where we're independent of the actual displacement of the car. If we have the car's mass and we have the car's velocities at two different points, then we can find out how much work is required because of the work energy principle. So the question is this: how much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? And so the approach that you should take here is to consider the car to be a simple object, because obviously a car is not that simple of an object. But if we just want to consider the car as a single object, as a whole system, then we can apply very simple physics to it, including the work energy principle. Right? So then what we're going to do is we're going to set out our work energy principle, which we have here. We know that the work required is going to be equal to the change in kinetic energy. That first expression is going to be the second kinetic energy, or the final kinetic energy. And that second expression is going to be the first kinetic energy. All right, so then I'm going to plug in the expressions that I know to be my quantitative definition for kinetic energy, 1/2 mv squared for each. And for the final kinetic energy, I'm going to apply my final velocity, which we have v2, 30 meters per second. And it's going to be leaving me with this expression once I plug in my values in my units. And I'm going to subtract my initial kinetic energy, which is the kinetic energy that I have from my initial velocity of 20 meters per second. All right? If I go ahead and grab a calculator and plug all that in, then what I'm going to get left over is 2.5 times 10 to the 5th joules. Now, that's a lot of joules, but it takes a lot of work to move a car, of course. All right? And that's a very simple example of how you use the work energy principle. There's another example on this PDF that I'll have linked below that you can look through on your own. The approach and the solution are there, as well as a few practice problems listed at the bottom. Solution videos for those practice problems should be posted by now. You can go ahead and get started working on those. If you need any help, feel free to send me a message. Good luck studying, and I'll see you guys in the next one.